Folks, welcome back for part 2, and we're going to jump right into section 2.5 and high energy electromagnetic radiation. Some definitions off the bat. Electromagnetic radiation is light, so it's just a fancy word, scientific word for light, and it can be described as energy that travels through space as a wave. So it's just energy traveling through space. Different light waves have different wavelengths. So we mean like different colors have different wavelengths. Things like X-rays or radio waves have different wavelengths. And the wavelength is the distance from the top of one wave crest to the next. So when you say that energy that travels through space as a wave, it can be described like a sine wave. There's some amplitude through space as it moves through space. So this could be x in space. This distance is the wavelength. And the wavelength describes we would call type of radiation. So radio waves, for example, would be very long wavelengths. And gamma rays be very short wavelengths. Okay, that's the idea. So electromagnetic radiation is light, and there's a whole spectrum of different wavelengths. The visible region that we see with our eyes being just but a sliver of the entire length. So we can see some relationships here. Down here at this end, we have high energy and short wavelength. So wavelength increases. So short wavelength like gamma rays and high energy. And at the other end, we have low energy and long wavelengths. Okay. Now, much different than what I just drew, but that's just an example. Because we can see, actually, this is 10 to the 12, and this is 10 to the minus 2. So that's a difference of 100 billion times. Way down here are X-rays in the 10 to the minus 2 nanometers. So we're talking picometers. And all the way up here at 10 to the 12, that's up to kilometers. So radio waves that have wavelengths of kilometers. And in this little sliver here at about a couple hundreds of nanometers is all of the visible light that we see. Around 400 nanometers in wavelength is purple, up to about 750 nanometers is red. And so you can see beyond red is called infrared, and beyond violet is called ultraviolet. So ultraviolet light has higher energy than visible. Higher yet is X-rays, and higher yet energy is gamma rays. But fundamentally, X-rays are no different than the visible light that we see. The only difference is the wavelength, and that our eyes are not able to differentiate or to see that wavelength. They're not sensitive to that wavelength of light. So another thing, when it says radio waves, this actually means radio waves, right? Like that you tune your radio dial and you hear sound. That sound is being transmitted through space as electromagnetic radiation with radio wave wavelengths. If you turn your radio to like, say, 102.9, that's actually 102.9 megahertz, and a mega is 10 to the 6, right? So that's the frequency that you're tuning your radio dial to. The AM stations, like 800 AM, those would be 800 kilohertz. So that'd be in this region of the spectrum. Okay, so very long wavelength, very low energy. But again, fundamentally, no different than the visible light that we see or X-rays that we use in medicine, other than the wavelength is different. Here's another way of showing that relationship between wavelength and frequency. So electromagnetic radiation is a form of energy that travels at the speed of light as a wave through space. And if you have shorter wavelength, that corresponds to higher frequency, and that also corresponds to higher energy. Mathematically, the curvature of the wave relates to energy, and so something that has more waves is more highly curved. But if you just remember short wavelength, high frequency, high energy. At the other extreme, longer wavelengths, lower frequency, lower energy. Say that wavelength and energy is inversely proportional. So the energy of light waves is inversely proportional to the wavelength. And so then high energy, short wavelengths can cause biological damage, right? Like high UV light causes sunburns. And so UV light from the sun would cause sunburns, but past UV is X-rays and gamma rays, and these would be even more damaging. So they're ionizing radiation, which means that they can dislodge valence electrons from atoms. Remember that valence electrons are the outermost electrons, the highest energy levels, and if electrons are lost, the charge changes and we get ions. So that's why this is called ionizing radiation. Okay, here's a question. Select the best match to the phrases from these forms of electromagnetic radiation. So each of these is the answer to A, B, or C. So go ahead and pause it and figure out which ones. All right, so lowest energy is radio waves. Next, less energy than visible light, but more than radio waves. I didn't actually mention that one yet, but microwaves, as we saw on the spectrum. And then finally, gamma rays cause the greatest damage. This is the Greek letter gamma. Okay, here's a multiple choice question. Select the correct statement. So you have to read these carefully. Go ahead and pause it and read them and figure out the correct answer. Okay, now that you're back, we know that visible light waves have more energy than radio waves. All the rest are false. So we can use this figure. And remember, you'll have access to this figure for any questions that you might need or have. And we see that visible light has more energy than radio waves. And all the other options are false. Okay, so the high energy radiation we have been calling ionizing radiation. Alpha and beta have to do with topics that are brought up in section 2.4 that for now we just need to know that they're high energy ionizing radiations, but this also includes gamma rays, X-rays, and the high end of ultraviolet, right? And so this means, again, that they have sufficient energy to dislodge valence electrons from atoms. Now, creating ions within cellular organs may lead to mutations. So this can lead to changes in the DNA of organisms. And these mutations may affect the reproduction of cells and may actually lead to rapidly reproducing cells, right? Rapidly reproducing cells is also known as cancer. So often radiation badges would be worn by medical personnel to monitor exposure for radiation. Because often if you're exposed, you don't know it right away. So we have a device, which is basically a detector that monitors the amount of radiation exposure. Now we can protect ourselves from this radiation. Like if you go and you get an x-ray, you'll probably be covered with a lead jacket or vest, or some other parts of your body besides what's getting imaged would be covered with lead, because a thin piece of lead is enough to block and absorb x-rays. However, it's not enough to block gamma rays, which are higher energy, but just a thicker piece of lead will do that. So alpha particles and beta particles are also ionizing radiation. Alpha particles can be blocked with a piece of paper. A piece of paper or clothing would certainly not block X-rays, but is enough for alpha particles. Beta particles can be blocked by aluminum. So this is one way to protect yourself. And also think about the factors that affect biological damage. And that would include the energy of the radiation and also the penetrating power. So the penetrating power is what we're showing here. This is penetrating power. So higher energy and more penetrating power are factors that can affect biological damage from radiation. Okay, let's stop part 2 here and we'll come back and continue with part 3.